Hey guys, so in this lesson, we're going to talk about solving polynomial equations. We already kind of know how to do that based off of how we've been solving quadratics. So we're going to still use those key ways of doing that. So let me move this up a moment. So here we go. Zero product property. That's going to be our main way of solving these polynomials. And again, we did that with quadratics. All you have to do is get it to be completely factored, which is what we were working on last section. And then all you do is set each factored piece to 0 and then solve. And again, the stuff we've done with quadratics, we've already practiced all of our ways of factoring with larger polynomials. So we're just going to continue using all of those skills. So in this example here, we have a cube root or a cubic polynomial. There we go. And I was able to factor out a GCF of 2x. Then was an easy enough trinomial for me to factor. Factors of 9 that add to -6 are -3 and -3. And then I was able to set each term equal to 0. You have to include your GCF as part of that. So 2x equals 0, x minus 3 equals 0, and then another x minus 3 equals 0. And we get our 3 solutions, 0, 3, and 3. And you notice 3 is a duplicate. And it's completely fine to leave both of those answers there. In fact, I would encourage you to do that. However, we now have this new term we're pulling in called multiplicity. So if you have something that repeats itself, it has a multiplicity of however many times it repeats. So in this case, we have a multiplicity of 2 because x equals 3 appears twice. Okay. So again, if you see that terminology multiplicity, it just means that solution repeats however many number of times. Okay, and again, we'll go through some of these ways of factoring and solving in class. Now, real quick with number 2, just make sure you get it equal to 0. You always have to have your polynomials equal to 0 before you can begin factoring and solving. Okay, so that's really important. So now what we're going to do with these solutions is get into graphing. And obviously, yes, we can use Desmos, we can use our graphing calculator to help us out, but knowing these tips and tricks on how to graph these polynomials is going to be really important because we know not all the time we have access to these, right? You can have a non-calculator portion of the NJSLA, and you might need to sketch it by hand. So first thing that you're going to do is you want to solve the polynomial, get those zeros. Those zeros are your roots, they're your x-intercepts. So you get that first. You can get your y-intercept first too if you want. Y-intercept's easy, it's your constant value. So it's 0, comma, the constant, whatever it may be. Your x-intercepts are your roots, your solutions. Now here's a few things about that multiplicity that I talked about. If you have an odd multiplicity, more likely than not, it might only appear once. That's an odd number. That means it's going to cross through the x-axis. So if this is my x-axis and it has an odd number, an odd amount of times it appears, it's going to cross through it. If it's an even, it's going to touch it and bounce back. So it's not going to cross it. It'll just sit on it, either above it or below it. It will touch it but never cut through at the point that has the multiplicity of even numbers. Again, usually we see multiplicities of 2, but there can be more. So just be aware of that. And the last thing is we want to note our end behaviors. Because if we're sketching the graph by hand and we don't have a calculator to look at and reference, we need to be aware of where are these ends pointing. So again, remembering that odd functions follow linear slopes and even functions follow our quadratics, right? Positive quadratics are upright, they're upright U's, they're smiling at you. Negatives are down, they're frowning, okay? And again, you can see how I went through this full problem here. Started by finding the zeros. I ended up having both solutions having a multiplicity. X equals -2 and an x equals 2 both appear twice. So that tells me it's going to touch. And you can see in the graph that what that means is it touched at -2 and +2, and then it bounced right back down. Now, what I tend to do is I will plot all my intercepts first, your x-intercepts and your y-intercepts, because those are going to be your hitting points that you want to make sure you touch. The end behavior is a negative even function. So it tells me both ends have to go down. So when I sketched this graph, I found my two outermost points, which were 2 and -2, and I got those end behaviors down. I started with that. And then I just connected the points in between there. Do I know if there's anything happening else in between? No, I don't. But I do know these intercepts, and I know that gives me enough to be able to sketch the graph of the polynomial. And again, we will go through this problems in class, and I will probably send the videos of me going through those as well. Okay, irrational root theorem. Really important because not all of our roots are going to end up being whole numbers. Not all of our roots are going to end up being rational numbers. They might be square roots, or they might be imaginary. So all things that we want to take a look at as we start solving these. So the rational root theorem says if you take your leading coefficient and your constant and you divide them, you set up this fraction, constant over leading coefficient, the factors of each term will create a list of possible solutions. Doesn't mean that every number that I list out is going to be a valid answer, but it does tell me a list of possible solutions that could work. All right. And what we're going to end up doing more often than not is setting up to get the possibilities, because that's what's going to ask you first. What are the possible solutions? And then we're going to use our graph, either a graphing calculator or Desmos, to help us narrow it down. So in this problem, Q, your denominator, is always your leading coefficient. So that's a 1. P is always your constant. So in this case, it's a 20. And then you list all the factors. It's up to you how you list the factors. I tend to think in pairs. So 1 and 20, 2 and 10, 4 and 5. Some people like to list them numerically. Completely your choice. Factors of 1 are 1. And then you split each one up. 1 over 1, 20 over 1, 10 over 1, 4 over 1, 5 over 1. And those become your possible roots. And it's always positive and negatives of those. Once you get your list, you want to narrow it down because that is a possible 1, 2, 3, 4, 5, 6, 12 numbers. And I surely don't want to test 12 numbers. So you graph it. This is the graph. And you narrow it down. So I can clearly see these points right here have to be solutions. That's what I wrote. The graph shows x equals -1, 4, and 5. And then you just have to show the work as to, are those in fact the correct solutions? And are there any more? Because there could be more you just don't see. So you use synthetic division to help you out, right? You test one, doesn't matter which one. You put it in, you factor the rest completely, and then you solve it. So in the end, I was able to get all the points I saw on the graph were the solutions to my factored polynomial. What may happen is you might have to do synthetic division a couple times in order to get to a point that you can factor. And we'll see more of that a little bit later on, especially once we start building up into polynomials that have more irrational or imaginary roots that we can't fully see right in the picture. And again, we will go through all of this in class. And this is what I was just talking about. Once we have our rational roots, you want to use a graph to help narrow it down. So in some cases, though, you might not know exactly what this number is. So this is going by 1, so -1, -2, -3. It could be -2.5, but I don't know. It might be -2.6, might be another decimal. I don't know. So that's why using whole number answers, like we clearly would see a +1 here, to help us narrow down what the other solutions could be is really important. Same thing over here. We're not quite sure what these decimal answers might be, but I can use the +4 once I start narrowing down my list and my synthetic division to get to a point of factoring that I can then solve completely. Our next thing is what we call the irrational conjugates theorem. So this is going backwards. And we've done this with quadratics. I've given you the solutions of a quadratic, and you went backwards and was able to write me a given quadratic that they came from. So what we have to be aware of is that with irrationals, remember when you square root anything, you have a positive and a negative of it. So if they give me a plus square root of b, some complex number that's a plus square root of b, I have to make sure I also include a minus square root of b. Otherwise, I don't have all the solutions. And I do that purposely to make sure that you're aware that you have the positive and the negative of all square roots. Okay. So again, simply saying if I have 3 plus radical 2 as a given solution, I must also include 3 minus radical 2. And again, the whole reason this is brought up is because we're getting into writing polynomial functions of least degree, meaning we don't know if there's any extra stuff happening. So we can only assume based off of how many answers we have. And we use them by coming up with the factored form and then multiplying it out. So for example, x equals 2 comes from x minus 2, right? All the ways of solving that we did before. Remember, it's basically the opposite of where it came from because you want to make it equal 0. So if I have x equals 2, I would subtract 2 from both sides to get it equal to 0. And now I have x minus 2, and that's the parentheses of the factored form it came from. And then again, we would multiply it out. So for instance, if I have x equals 2, x equals 5, and x equals negative 7, these are the zeros they told us. We're going to start by writing it in factored form. There they all came from. They're opposite signs. And then you multiply it out. It doesn't matter. You can only do 2 at a time. So if you want to do the first 2 and then the last one multiply in, whatever you want to. I chose to do the last 2 and then multiplied x minus 2 in. Regardless of the order you do it, you can only do 2 at a time, and then you clean up everything by combining your like terms. So in the end, this was a 3rd degree polynomial, had 3 zeros, and this is what it came from. Now in the next example, it includes our radicals. Okay, so again, they just still come from a positive square root came from an x minus square root of 2. A negative square root came from an x plus square root of 2. A shortcut for your multiplying. This will come in handier. Yes, there you go. Handier once you start getting things like 2 plus radical 2 or 4 plus radical 7, something where you have numbers being added or subtracted, that complex number. You're going to group together all whole values. So in this case, x is considered a whole value. So I group them together and square it because there's 2 of them. Then I group together any radicals. So the square root of 2, square root of 2, grouped it, it's squared because there's 2 of them. And you use a minus sign because you had a positive and a negative. Positive times negative comes out to be a negative value. Sorry about that. So from there, you then multiply it out. X squared is just x squared. If there was more to multiply it out, you would. Square root of 2 squared is just 2. And that's the reason we group those together. Because if I group the radicals together, the square is going to cancel them out. And the fact that they're opposite signs is why we put a minus sign here. And then again, you multiply it out to get your completed solution. Okay? And again, we're going to go through a lot of these problems, as you can see, throughout the end of the practice. And again, I will most likely post another video of me going through at least a few of those to get more examples to you, as well as the ones we're going to practice in class.